Welcome to Crash News. Ever feel like your phone or laptop is lightning fast?
Oh, yeah, they feel pretty quick these days.
Well, buckle up, because we're about to talk about something that could make even supercomputers feel like, I don't know, an abacus.
Haha, right. We're talking a whole different league.
Exactly. Today, we're diving headfirst into a potentially revolutionary announcement. Microsoft says they've created the world's first quantum processor powered by something called topological qubits. It's named Majorana-1.
Majorana-1. Yeah, big news in the quantum world.
And this isn't just, a slightly faster chip. It seems like a completely different way of thinking about computation.
It really is a fundamentally different approach.
You sent us a fascinating stack of articles on this, and our mission today is basically to unpack what this news really means. Why are these topological qubits suddenly such a big deal? And, is this the dawn of a real quantum future? Or maybe just another interesting step on what seems like a very, very long road?
That's the key question, isn't it? Hype versus reality.
We're going to try and break down the complex science bit by bit. We'll use some analogies, maybe a fun fact or two, just to keep things engaging.
Sounds good. Analogies definitely help with this stuff.
Think of it like this. The computers you use now, they work with bits, simple on or off switches, 0 or 1.
Right, classical bits. Very straightforward.
Quantum computers, though, use qubits, and these are way more flexible. They can be on, off, or somehow, both at the same time.
That's the weird part, yeah, superposition.
But the catch has always been that these qubits are incredibly fragile, delicate.
It's extremely delicate. That's been the Achilles heel.
Or at least they were, potentially. Microsoft's approach is considered a real moonshot in the quantum world.
It is. Very ambitious, high risk, potentially high reward.
So we're going to explore why that is. Let's start right at the beginning. What even is quantum computing, and why should you, our listener, care about it?
Okay, yeah, perfect place to start. So our classical computers, the ones in our phones, laptops, even massive data centers, they're amazing for most things.
Sure, emails, spreadsheets, games.
Right. But there are certain problems, really complex ones, where even the biggest supercomputers just hit a wall.
Like what kind of problems?
Imagine trying to design a totally new material, predicting exactly how every atom will behave, or simulating precisely how a complex drug molecule interacts with proteins in your body.
Okay, yeah, that sounds incredibly complex.
It is. For some of these problems, a classical computer would literally take longer than the age of the universe to find the answer. They just can't handle that level of complexity efficiently.
Wow, okay. So you just grind to a halt.
Pretty much. And that's where quantum computing comes in. It offers a completely different way to tackle these currently, impossible problems.
And then the payoff could be huge.
Think about it. Designing self-healing materials from the ground up, or developing hyper-efficient fertilizers for more sustainable agriculture. Discovering new medicines or safer industrial chemicals without years and years of lab work.
Those are some massive potential breakthroughs.
Exactly. These are the kinds of things quantum computing promises to unlock someday.
Okay, so what makes them so different? You mentioned qubits instead of bits. Let's break that down.
Right, so classical bits are simple, either a 0 or a 1, on or off.
Got it. Binary.
Quantum computers use qubits, and qubit, because of quantum mechanics, isn't forced to be just a 0 or a 1. It can exist in a combination of both states simultaneously.
Both at once. How does that even work?
It's a quantum phenomenon called superposition. Think of it like a spinning coin before it lands. It's neither heads nor tails. It's kind of both until you measure it.
Okay, that's a bit mind-bending. So this superposition is the key.
It's one of the keys, yeah. This ability to hold multiple values at once allows quantum computers to explore a vast number of possibilities simultaneously for certain types of problems.
So instead of checking paths one by one like a classical computer.
The quantum computer can effectively check huge numbers of them all at the same time. That's where the potential for incredible speedups comes from.
For specific problems, though, right?
Yeah.
Not for everything.
Exactly. It's not going to make your web browsing faster necessarily. It's for these really complex simulation and optimization problems. But there's a big but.
I sense the catch coming, the fragility thing.
You got it. This quantum superposition state is incredibly delicate. Qubits are like divas. They need perfect conditions.
Fragile, how so? What makes them so difficult to work with?
They are extraordinarily sensitive to their environment. Even the tiniest disturbance, a little vibration, a stray bit of heat, a tiny fluctuation in a magnetic field can knock them out of their quantum state.
So they just stop being quantum.
Pretty much. It's called decoherence. The Qubit loses its superposition, its quantum magic, and collapses back into behaving like a regular old 0 or 1.
And then you lose the whole advantage.
Boom! Calculation ruined. It's like trying to build, I don't know, a delicate ice sculpture in the middle of a heat wave.
Okay, I see. So building a stable, reliable quantum computer is a massive challenge because of this decoherence.
It's arguably the biggest challenge the field faces, keeping these qubits stable long enough to do useful calculations.
So this is where Microsoft's approach comes in, being different. They're trying to tackle this fragility head-on with topological qubits.
Precisely. While lots of other very smart people at places like Google, IBM, and various startups are making really good progress with other qubit types, like superconducting circuits or trapped ions.
Right, I've heard of those.
They're essentially trying to build better and better refrigerators and shielding to protect those fragile qubits and developing complex error correction codes.
Okay.
Microsoft took a step back, maybe over a decade ago, and pursued a radically different path. Their idea was, what if we could build a qubit that is inherently protected from noise?
Built-in protection.
Yeah. Using principles from a field of physics called topology. It's like,
Yeah.
instead of building your house on shifting sand and then trying to engineer earthquake-proof walls, Microsoft decided to find bedrock first.
That makes sense. So this was a long-term bet for them.
Oh, absolutely. They set up Station Q back in, I think it was 2012, a dedicated research group purely focused on making these theoretical topological qubits a reality. It's been a long, hard road.
So let's get into these topological qubits. What makes them different? What is this topological protection?
Okay, the core idea is to encode the quantum information, the zeros and ones, and the superposition state, not in a single, easily disturbed property, but in the overall structure, the topology of the system.
The topology. Like the shape.
Kind of, yeah.
Ah.
Think about a coffee mug versus a donut. Topologically, they're the same. They both have one hole.
Okay, I think I follow.
Now imagine you slightly squish the donut. Still has one hole, right? The property of having one hole is robust against small local changes. It's protected by the overall shape.
Ah, I see. So the information isn't easily erased by just poking it a little bit.
That's the concept. Topological qubits aim to store quantum information in these protected features, making them naturally resistant to local noise and disturbances that would easily kill a conventional qubit.
That sounds incredibly clever if it works. So how do they actually do that? I keep seeing this term, Majorana-1 modes, MZMs. Sounds like something out of science fiction.
It does, doesn't it? It's pretty exotic physics. Majorana fermions are these weird theoretical particles, or rather quasi-particles in this context, that are their own antiparticles.
Your own antiparticle. Okay, that's weird.
Yeah, it's mind-bending stuff. But the crucial thing is that under very specific, very carefully engineered conditions, pairs of these Majoranas can appear at the ends of tiny, specially made wires. These are the Majorana-0 modes, the MZMs.
And these MZMs are the key.
They are the building blocks. Think of a pair of MZMs at opposite ends of a wire as encoding one bit of quantum information. But the information isn't located at one end or the other. It's sort of smeared out, shared non-locally between them.
Shared between them.
Exactly. And because it's non-local, a local disturbance, like noise hitting just one end of the wire, can't easily destroy the information. It's protected by this topological property. It's like having a secret stored in two different safes. You need to access both correctly to get the whole secret.
Okay, wow. So Microsoft's Majorana-1 chip is actually built using these things.
That's the claim. They say Majorana-1 is powered by a topological core architecture built using these MZMs.
How did they manage to create them? It sounds incredibly difficult.
It is. It involved a massive materials science breakthrough. They had to create a whole new state of matter called a topological superconductor.
A new state of matter, like solid, liquid, gas,
Yeah.
topological superconductor?
Sort of, yeah. It's an exotic quantum state. They did this by combining specific materials, typically a semiconductor like indium arsenide and a superconductor like aluminum, in very precisely structured nanowires.
Nanowires, so incredibly tiny wires.
Extremely tiny. Then they have to cool this whole thing down to temperatures just fractions of a degree above absolute zero.
Minus 273 Celsius, that cold.
Pretty much, yeah. And apply incredibly precise magnetic fields. Only when all these conditions are just right do these topological superconducting nanowires form, and the MZMs are expected to appear at the ends.
Man, that sounds like an engineering nightmare. The precision required must be immense.
Absolutely monumental. It's taken them years and years of painstaking work just to get the materials and the device fabrication right.
Okay, here's a fun fact I read. A single qubit is encoded in a pair of these Majorana modes, right? And the information is delocalized.
That's right. The quantum state, like whether it's a 0 or 1 or both, isn't just sitting in one spot. It's shared across those two separated Majorana modes at the ends of the wire. It's this delocalization that provides the topological protection.
Truly bizarre. Okay, let's do a quick pop quiz for you listening. Based on what we've just discussed, what are those special quasi-particles, those exotic things at the heart of Microsoft's topological qubits?
Give you a second to think.
Got it.
The answer is Majorana 0 modes, or MZMs.
Nice one. So, okay, they've potentially created these MZMs in the Majorana-1 chip. What are the key innovations here? What makes this chip special?
Well, the biggest innovation is arguably demonstrating this topological core architecture actually working even at a small scale, creating that specific topological state of matter on demand in a chip.
The foundation itself.
Exactly.
Yeah.
This state is what allows the MZMs to exist and, crucially, shields the quantum information they encode from noise. It's like building that soundproof room we talked about earlier.
Right.
And because the information is stored in this tricky, spread out, topologically protected way, it's just inherently harder to mess up accidentally, like a really well-encrypted message.
And I also read the chip itself is physically quite small.
Right.
Palm-sized.
Yeah, the reports suggest it's remarkably compact compared to the installations for other quantum computers. You often see pictures of these huge chandelier-like structures hanging in massive refrigerators that take up a whole room.
Right, those dilution fridges.
Exactly. If Majorana-1 is truly palm-sized, even with its necessary cooling, that's a big step towards practicality. You could potentially imagine these fitting into standard data center racks eventually.
That's a huge potential advantage for actually using these things.
Absolutely. Practicality and integration are key.
So if this topological approach really pans out, what are the main advantages over, say, these superconducting qubits that IBM and Google are working on?
The biggest promised advantage is stability, leading to much lower error rates. Because of that built-in topological protection, these qubits should be far less prone to decoherence.
Less likely to pop.
Right. And if your basic qubits are more reliable, you need much less overhead for error correction.
Error correction.
Yeah.
That's where you use lots of physical qubits just to make one reliable logical qubit, right?
Exactly. Other approaches might need hundreds, maybe thousands, of noisy physical qubits to create one stable logical qubit you can actually compute with. Topological qubits, if they work as hoped, might drastically reduce that ratio. Maybe 10 physical for one logical, or even better eventually. That's the dream.
Wow, that would make scaling up much more feasible.
That's the second major potential advantage. Scalability. If you need fewer physical qubits per logical qubit, and the chip design itself is potentially more compact, it offers a clearer path towards building machines with millions of logical qubits someday.
Going from that skateboard to a rocket ship, as the analogy goes.
Something like that, yeah. It tackles the error problem fundamentally rather than just trying to manage it with brute force.
And the third advantage you mentioned was practicality.
Right. The smaller size, potentially simpler control mechanisms compared to managing thousands of error-correcting qubits could make it easier to integrate these processors into existing infrastructure, like Microsoft's Azure cloud.
So you could actually rent quantum compute time online, making it accessible.
That's the vision. Democratizing quantum computing power, making it available to researchers and companies without them needing to build their own quantum data center.
Okay, this is painting a really exciting picture. If Majorana-1 or its successors live up to this potential, what kind of real-world problems could they actually solve? What are the implications?
The possibilities are pretty staggering across many fields. We touched on material science, designing new catalysts for greener chemical processes, better materials for batteries or solar cells, maybe even room temperature superconductors eventually.
Room temperature superconductors, that would change everything.
It would be revolutionary. Then there's drug discovery. Simulating how potential drug candidates interact with targets in the body could slash development times and costs. Maybe lead to truly personalized medicine based on your specific DNA.
Designing drugs specifically for individuals. Wow.
It's a long-term goal, but quantum simulation could enable it. Climate modeling is another huge one, creating much more accurate predictions of climate change and its impacts.
Better models mean better decisions, hopefully.
Hopefully. Financial modeling, too, optimizing complex investment portfolios, pricing exotic derivatives, assessing risk much more accurately.
Okay, finance too. What about AI?
AI is a big one. Quantum machine learning algorithms could potentially process data in fundamentally new ways, maybe leading to breakthroughs in pattern recognition or optimization tasks that are beyond current AI.
It really does sound like going from, I don't know, a bicycle to a supersonic jet for certain really hard
That's
problems.
a pretty good analogy, yeah. For the right kind of problem, the jump in capability could be that dramatic.
So how does this compare directly to what others are doing? You mentioned IBM's Condor chip with over 1,000 qubits, Google's Sycamore or Willow. They have more qubits now, don't they?
They do have significantly more physical qubits right now, yes. IBM's Osprey had 433, Conor hit 1,121. Google has demonstrated quantum supremacy with fewer qubits but complex circuits. These are incredible engineering achievements.
But they're using the more fragile type.
They're primarily using superconducting transmon qubits, which, yes, are inherently quite sensitive to noise and require substantial error correction. It's a numbers game combined with sophisticated error management.
So Microsoft's approach is fundamentally different in philosophy.
Exactly. It's quality over quantity, initially at least. Microsoft is betting that achieving inherent qubit stability, even with fewer qubits to start, is the better long-term path to building a truly scalable, fault-tolerant quantum computer.
Like building with bricks versus building with, I don't know, soap bubbles that you constantly have to patch up.
Maybe. Or maybe like comparing those delicate glass figurines to more robust rubber balls. The goal with topological qubits is to make the fundamental component much tougher. Focus on the foundation so you can build the skyscraper later.
And just demonstrating this, even with a few qubits, is a big scientific deal itself.
Oh, absolutely. Forget the computing aspect for a moment. If they have truly created and controlled Majorana zero modes and demonstrated topological protection, that's a Nobel Prize-worthy discovery in fundamental physics. It would be the first experimental confirmation of a new phase of matter and a way to encode information predicted by theorists decades ago, using these exotic things called non-abelian anyons, which Majoranas are an example of. It validates a whole field of theoretical physics.
Now, we should probably address the history here. I remember some controversy. Wasn't there a paper claiming Majoranas that got retracted a few years ago?
Yes, that's crucial context. You're right. Back in 2018, a team from Delft University, collaborating with Microsoft, published a high-profile paper in Nature claiming strong evidence for MZMs.
Big news at the time.
Huge news. But later, other scientists raised serious questions about the data analysis. Eventually, after intense scrutiny and reanalysis, the authors themselves retracted the paper in 2021.
Ouch. That must have been a blow.
It was a significant setback and made the whole community, understandably, much more cautious and skeptical about any subsequent claims. It highlighted just how difficult these experiments are and how easy it is to see signals that look like Majoranas but aren't.
So Microsoft's Station Q team really had to go back to the drawing board after that.
They definitely spent the intervening years rigorously refining everything: their materials growth, the device design, their measurement techniques, and especially their data analysis protocols to be absolutely sure this time.
So this new 2025 paper underlying the Majorana-1 announcement, it faced extra scrutiny.
You can bet on it.
Yeah.
Reports suggest the peer review process for the new Nature Physics paper was exceptionally thorough. And interestingly, the paper itself is apparently quite cautious in its language.
How so?
It focuses on demonstrating the successful fabrication of the device, showing it can be tuned into the specific regime where topological superconductivity and MZMs are expected to occur, and presenting measurements consistent with theoretical predictions. But it stops short of definitively claiming we have created a topological qubit.
Okay. But then Microsoft's public announcement did claim the world's first quantum processor powered by topological qubits. That sounds like a stronger claim.
Exactly. There's a noticeable gap between the careful, nuanced language typically found in a peer-reviewed scientific paper and the more assertive claims in the press release and marketing materials.
Why the difference?
This has definitely been a point of discussion in the scientific community. The ideal is that public claims are fully backed by the peer-reviewed evidence. Microsoft's explanation, primarily through talks by Chetan Nayak, who heads their hardware effort, is that they gathered further decisive experimental evidence after the paper was submitted, but before it was published.
So newer data wasn't in the published paper.
Apparently so. NIAC has been presenting this newer data at conferences, showing results from tuning the devices, performing measurements they say confirm the topological phase, and even initial steps towards braiding operations, which would be key for computation. Their stance is the internal evidence is stronger than what made it into that first publication.
Okay, so it's a bit of a watch this space situation, waiting for more published details on that newer evidence.
Pretty much. The initial paper is a significant step, demonstrating the hardware platform, but the definitive proof of robust, controllable topological qubits is likely still unfolding in ongoing experiments and future publications.
Right, so where does Majorana-1 actually stand now? How many qubits does it have, and what's the outlook?
The initial reports stated Majorana-1 has 8 qubits. Now, 8 qubits, even if they're perfectly stable topological qubits, isn't enough to solve those world-changing problems we talked about. Not even close.
Okay, so still very early days in terms of scale.
Very early. Demonstrating the principle is huge, but scaling this architecture up to hundreds, thousands, or the envisioned millions of qubits presents enormous engineering challenges. They need to figure out how to manufacture these complex devices reliably, how to connect and control large numbers of them, how to perform quantum operations like braiding. It's a long road ahead.
Does Microsoft have a roadmap for this?
They do. They've talked about aiming for real-world utility and integration with Azure Quantum, their cloud platform, maybe in the late 2020s. The ultimate vision of a million-qubit machine tackling major industrial problems is likely something for the 2030s or potentially even beyond. It's a marathon, not a sprint.
Got it. Okay, one last pop quiz before we wrap up. We've used this word a lot. Why is Microsoft's approach called topological quantum computing?
All right, think back to that donut analogy.
Okay.
It's called topological because the quantum information is encoded and protected by the fundamental topology of the system, making it inherently resistant to local errors and noise.
Perfect. So stepping back, looking at the big picture here, what's the overall significance of this Majorana-1 announcement, even with all the caveats and the long road ahead?
I think it represents a really bold, ambitious attempt to solve the fundamental problem plaguing quantum computing. The trade-off between qubit quantity and qubit quality, or stability.
Trying to get both at the same time eventually.
Right. By focusing on building inherently stable qubits from the ground up. Whether they ultimately succeed in scaling this specific Majorana-based approach or not, the research itself is pushing the boundaries of physics, materials science, and engineering.
Learning things, even if the final goal changes.
Exactly. It's driving our understanding of these exotic quantum phenomena and forcing innovation in measurement and fabrication. It really is this amazing convergence of so many different scientific and engineering disciplines.
So this tiny chip, Majorana-1, it holds a lot of potential, a lot of hope, even if it's just the beginning.
Immense potential, yes. It's a crucial first step, perhaps, on a path towards quantum computers that could genuinely move out of the labs and into the world to tackle challenges we can barely even imagine solving today. 8 qubits won't change the world tomorrow, but it might just be the cornerstone of a technology that could.
Okay, so what does all this mean for you, the listener, trying to make sense of it all?
Well, Microsoft's Majorana-1 chip is definitely a fascinating development. A real glimpse into a possible future of quantum computing that's powerful and stable. Yeah, it's one possible future and a very interesting one.
It also really highlights how science progresses, right? There are these bold claims, huge excitement, but also rigorous scrutiny, careful checking, and sometimes, setbacks and debates along the way.
That's the scientific process in action. Healthy skepticism is key.
Hopefully, this deep dive is giving you a clearer picture of what topological qubits are all about, the science or the claimed science behind Majorana-1 and why it's got people in the quantum field talking so much.
There's definitely a lot to talk about.
Now, if your curiosity is piqued and you want to go deeper, we've really just scratched the surface here. Quantum computing is a huge field.
Oh yeah, rabbit holes galore.
You could read up more on superposition, entanglement, another key quantum concept we didn't even get into much, or these topological phases of matter, the whole history of quantum computing. It's fascinating stuff.
Definitely worth exploring if you're interested.
And if you enjoyed this breakdown, if you like these deep dives into complex, sometimes confusing, but important topics, there are a few simple, free ways you can support the show.
Yep. Always appreciate the support.
You can rate and like us on whatever platform you're listening on right now. That really helps other people discover the show. Hit subscribe so you don't miss our next deep dive.
Takes just a second.
We also have a growing community over on Discord where you can chat with other listeners, ask questions, continue the conversation. The link for that is in the show notes.
Yeah, come join the discussion.
And finally, if you want to directly support the creation of more content like this, you can become a patron. All the details for that are also in the show notes. We appreciate any support you can offer.
Big thanks to everyone who does.
Okay, so here's a final thought to leave you with. If Microsoft's big bet, their moonshot with topological qubits, actually pays off down the line, how radically do you think that could reshape things? Industries, science, maybe even daily life. What currently impossible problems might suddenly become solvable? Something to ponder.
It's a fascinating question to think about. The potential is mind-boggling.
It really is. Thanks for taking this deep dive with us today. Until next time, keep exploring.